Bazak, who's now at PNNL as a staff scientist, he called this the grid, and it was the holy grail of his PhD thesis, and just came out last year, or 2020, in JEX. This data set allowed us to evaluate all of the transference number properties for the electrolyte under this range of conditions, and thereby create a database of how the ions transfer, both the lithium and the anion. And you see this really strong polarization when we have a high temperature and a strong current applied in the cell. This is still the pencil cell geometry. We went beyond this to the roto battery. This is the work of Annika Freitag, who graduated from the group and is now at the Humboldt University in Berlin. And she built this 3D printed construction to create these tiny jelly roll devices that fit within a rotor. And this is her table of contents graphic. I'm not going to walk you through the data, but the essence of it is we have resolution because we're applying magic angle spinning of the anode signal and the cathode signal independently, both in a full cell geometry. So this is kind of exciting, and we're still working on next steps with this technology. But of course, that doesn't look much like a lithium battery to most electrochemists. So in collaboration with Bruce Belcom's group at the University of New Brunswick, we've designed this parallel plate resonator geometry, which allows us to put a prismatic cell into the probe. And I give this picture partly as Joanna encouraged us to geek out about the tech pieces and the hardware pieces. This is a piece that we obtained from collaborators at Karlsruhe in Brucker from Klaus Sieg's group that allows us to combine our parallel plate resonator with the Brucker hardware in a robust fashion. It gives us a nice homogeneous field and reduces the RF attenuation effects in some of the other in situ geometries. And it also looks an awful lot like a prismatic lithium battery cell. So this is Andreas from the Belcom group. He did the simulations of the B1 field in that device. And this is what the device looks like in practice. What we do is slip a cartridge cell lithium ion battery within this parallel plate resonator to determine different properties of the cell. This is now the work of Kevin Sanders, who's a current postdoc in our group. And he was able to use this cartridge cell geometry to do both spectroscopy and imaging. This is the image of a polymer electrolyte using chemical shift imaging. So you can see that this tool is going to become quite robust. And in terms of our collaborations with industrial partners, one of the most important properties of lithium battery chemistry is when does the lithium plating occur? And it turns out that this device is really well suited to measure that. If we insert lithium into graphite at a very gentle rate, we can see the contour plot now is mapping out the spectroscopy of the evolution of the peaks. Kevin is a graduate of Phil Grandinetti's group where he did his master's. So he talked to Phil and helped us to implement the DOP, derivative operando strategy, that allows us to take the derivative of the contour map and therefore highlight where the changes are happening as we insert and then de-insert lithium from this graphite cell. And most importantly, we can cycle this cell at a high C rate and observe this plating of lithium within the cell. So the plating of lithium is so diagnostic in NMR because it's got this fingerprint way up at 256 ppm, separate from everything else. And so as we change the cycling conditions, we can force lithium plating in the cell. Whoops, sorry, wrong way. And then we can observe whether when we switch the potential of the cell, does that disappear or not? And some of it disappears and some of it actually remains constant. So the combination of the original spectroscopy plus the derivative spectroscopy give us a full picture of the lithium plating in this process. And this is all really interesting and great, but this is essentially now a tool that we can use to evaluate different electrochemical protocols. We also want to be able to evaluate new materials. And this is where I'm going to go back and look in detail at some of the work from Tayana Pereira. She's a current graduate student, and from now on, the data I'm showing you is not published yet. The material that she is studying is an iron vanadate structure. So we've got all of the paramagnetic complexities that make magic angle spinning the tool we need to apply to look at this phase. And electrochemically, it's quite beautiful. So it has some nice smooth plateau regions, then some phase transition regions, and it has a very nice reversible electrochemical process shown by the small hysteresis in this electrochemical cell. And at each of these data points along the curve, Tayana is going to take out the coin cell, disassemble it in the glove box, and pack it in the tiniest of these rotors in order to do magic angle spinning as fast as we're capable of in our lab. And what she observed is this puzzling phenomena that although our collaborators had given us a crystal structure of this material, said there should be 3 lithium sites, off you go, lo and behold, there are more than 3 lithium sites. And when we said, could you give us another material? We're not quite sure. They came back with different distributions of the population of essentially 2 sets of 3 lithium sites. And so this became a problem that Tiana and I really wanted to dig into. And so we looked first of all at the synthesis, and Tiana did her own synthesis. And it turns out that our collaborators at University of Montreal had created a single crystal to do their crystallography from a flux process, whereas the bulk material that we're doing the electrochemistry on is coming from a powder synthesis. And it boils down to, in the single crystal synthesis, we're doing a congruent melting process where we get a homogeneous structure, and not so in the powder sample synthesis. But this is still a robust synthesis that's giving a reproducible NMR pattern just with a changing distribution of these 2 sets of peaks. And so we wanted to look at it a little more carefully. So Tiana searched through the sample, found a single crystal, was able to do a diffraction experiment at our facility at McMaster. And what they determined was there's a small amount of twinning in the structure. So 15% of the vanadium-2 and the vanadium-6 move slightly in their crystallographic positions and occupy 85% the orange sites and 15% the pink sites in the structure. So that gives us 2 different ways for the local environment to contribute electron density from the vanadium into the lithium sites. And so now we wanted to think about deconvoluting this spectra as a set of 2 sets of 3, like I mentioned. So we have 2 parent structures. The orange one is the original CIF file from our collaborators in Montreal, and the pink is if we fully populated this new set of sites that Tiana had determined in the crystallography. So in order to understand why those chemical shift differences are happening, we rely on VASP, and this is in collaboration with Danny Carlier's group. What we did was 3 different calculations using the PAW method and applying generalized gradient approximation, so GGA, and also using the Hubbard interaction, or the +U term. This term in particular localizes the electron density at the transition metal centers and gives us a closer approximation of the experimentally observed shifts. And we use this method to calculate all of the lithium shifts in the structure in 3 different structural configurations. So we did energy optimizations of the original structure, the new structure that Tiana determined with fully the pink polyhedra, and then a mix, because we know that about 15% or 1 asymmetric unit of our full unit cell is populated by this new orientation of the vanadium centers. So the first thing you do is the geometry optimization. We walked through this. The experimental data for the 2 different structures are shown in the boxes. And the important thing to notice here is no matter which value, either GGA itself or GGA plus U with different values of the U factor, the volume of the unit cell, the overall unit cell structure is not changing significantly. So that's reassuring to us. We can go ahead now and calculate the chemical shifts of each of these structures. And what we see are 3 things. So lithium-1, of course, they don't label in the crystallography the same way that they do in the NMR. So lithium-1 is the middle peak in turquoise. Lithium-2 turns out to be the pink peak at the high frequency, 100 ppm. And we can see that when we just use GGA, these chemical shifts are significantly overestimated, but we add in the U parameter and the chemical shifts come down close to the experimental range. But in general, it's known that VASP overestimates the positive shift contributions. And in this particular occupation of our d orbitals, there's only positive chemical shift contribution, no negative chemical shift. So in the end, they average to be about 50 ppm above our experimental, but showing the same trend. So this is for the original structure. We then did the same thing with the new structure, fully occupying the secondary set of vanadium sites. And we see that that doesn't substantially change these chemical shifts. If we keep in mind that this difference between the experimental and the calculated is what we're going for, these are still within that realm for each of these new chemical shifts. But Tiana had noted, and I said, don't worry about it, it's a small feature, but she was always bothered by this chemical shift up about 300 ppm. And so we finally got a bit of understanding of what's going on here when we did the step of mixing the structure, so giving 1/8 of the asymmetric of the unit cell to this new vanadium position and the rest in the original. And that mixing of those two positions, which we think is what happens in the experimentally prepared samples, suddenly generates a chemical shift. So there's 3 groupings of the chemical shift. Each lithium is now split into 4 positions. There's one particular shift of the lithium-2 that's jumped out to above 300 ppm. And what does that shift represent? Well, it represents a different local environment for that lithium where there's more donation from the iron unpaired electron density into that lithium center. And this is just a visual for you of that. This is one example of all the rest of the lithiums which have 2 iron nearest neighbors within the 2.5 angstrom radius. And the lithium-2, that's the new species with a 3rd iron occupying the local coordination environment. So that's a very satisfying understanding of that crystal structure and how the synthesis is playing into what the NMR observables give us. We think this is a really important message that what you get out of one single crystal structure doesn't represent the bulk of the sample. And we heard some ideas around that yesterday as well. And so we went forward from here to then think about the structure and how it changes during the electrochemical process. So this is the electrochemical curve that I showed you. We've taken a spectrum at each of these data points going along. And the really significant change happens here at lithium 1.55, where everything broadens. And then all of a sudden, we have a new set of 3 peaks. And we had this data actually quite early on. Before we had done any of the structural investigation, we had this evidence of NMR telling us there's a phase change happening here, and there's a new kind of dynamics going on once we pass that phase change. What we did with this is examine this phase change first from the NMR point of view, looking at the local dynamics. So this is just simple XE experiments at 50 milliseconds mixing time for the original phase, and then the phase above that transition, so the electrochemically lithiated phase. We have nice evidence of chemical exchange around those 3 new that set of 3 peaks. And then we don't rely on XE to do this quantitatively because those experiments are really long. My group used a lot of selective inversion where we're simply flipping the C peak here and observing the change in intensity at A and B. And what we look for is this signature transient well that's indicative of chemical exchange or a loss of intensity from the A peak or B peak before it relaxes back to equilibrium as we go through this series of spectra. And we can do this whole data set in one evening, whereas we used to be getting 1 XE experiment per 1 evening. So this is a nice efficient process. And we fit this data using a program written by my colleague, Alec Bain, who passed away a few years ago, but we still know and love all of his work. This is the experimental data of the transient well evolving as a function of temperature. And we do the deconvolution to extract all of the exchange rates. Exchange rate increases with temperature as it ought to. And so this is self-consistent. And the exchange rate actually is changing as we increase the population of lithium in the structure. So you can think of this as a crowding effect. We go through a phase change, it opens up the lattice a little bit in a way that allows a new dynamic process, but then we're adding more lithium into that structure and populating it in a way that's actually blocking the pathways for lithium conductivity as we continue lithiating the structure. And that shows up for us in a crowding effect, which causes an increase in the activation energy. Tiana has done a mountain of work to deconvolute this. I don't want you to read every data set, but just to give you a sense of the amount of effort here. And the A, B, and BC activation energies systematically increase as we lithiate. The AC is a bit scattered, and I'll point out to you the error bars here. What's going on is when you invert the middle peak and you try and observe the intensity side to side, there's a bit of an error associated with that. But we're sort of honest about that, and the trend looks really robust. And the other thing we want to do then is understand the phase change that's going on that's leading to this change in dynamics. And the way that Tiana has done this, and this is data from the synchrotron, the Canadian light source in Saskatoon, where she's actually collecting high resolution X-ray diffraction data as she inserts lithium through this phase change. And we haven't done the full evaluation yet, but this shows you there's a volume change. Each of the A, B, and C parameters of the unit cell are changing, and we're just in the process of evaluating that data set now. So with that, I'd like to thank you for your attention. Thank Tayana here at the front, who did the majority of the work, and our collaborators. And I'll just mention, we do have a postdoc position available in the group. If you're interested, I'd be happy to chat. PhD positions as well. We were talking about recruiting students as a challenge post-pandemic. So if you're interested or you know people who might be interested, I'd be glad to hear from you. Thanks very much.
Thank you, Jillian. So questions, and we always like to encourage questions from students and postdocs.
Really nice talk. I have a question on those transient wells that you were observing in the lithium exchange experiments. In those cases, I'm not sure whether there are any uncertainties or what is the level of uncertainty in estimating the exchange rates in this type of method. So just curious, have you also considered trying like a selective saturation type experiment and just watching the saturated signal just get filled in or something of that sort?
It's an interesting suggestion. So we give quite honest error bars, I would say. I really insist with my students that the error bar represents the quality of the deconvolution as well as the fit. So the software provides us an error bar in the fitting routine. What I would say is you can see the depth of the well increasing. So we're confident that this is a reproducible result. If I thought about your suggestion around saturation versus inversion, saturation would mean we sort of start here and go up. So it would compromise the dynamic range a little bit. And I'm not sure whether there would be a benefit because you would still be using a selective pulse to create that saturation. But maybe there's a way to do that that I don't know about. I'd be glad to hear if there's the key is, can we make the pulse really selective and not compromise the time frame of doing the experiment because dynamics are happening during the pulse.
What sort of pulses are you using for this selective inversion?
It's just a regular Gaussian 180-degree pulse.
I see. Just one final question about your chemical shift calculations. In those cases, I see that you had this overestimation consistently from the calculation. So have you observed any trend in any of the principal components at all? Just out of curiosity, like is the delta 1,1, is that the component that's consistently being overestimated from the calculation?
I know what you're asking, but I would have to look at the data.
No
but thank you. That's a good question.
Thank you.
Yeah.
Yeah, Paul.
I'm a great fan of complementarity. So have you considered looking at the vanadium NMR since you can spin fast and do all that? You should see that.
Yeah. I am not very brave about big quadrupoles plus paramagnetism. So that's been my sort of default. But if you have a suggestion, you're clearly the expert. So
plus or minus a half. Go for it.
thank you. Sorry.
I had a question about your prismatic cell measurements that you showed at the very beginning.
Yep.
Were those measurements done on single layer cells or were they multi-layer cells?
They're single layer cells.
Okay. Have you thought about doing these for multi-layer cells, or what kind of challenges would you expect in those kinds of configurations? Maybe you have to like fold them properly and
yeah, the biggest challenge I would say if we went to multi-layer is you get a bigger and bigger attenuation of the RF penetration by the conducting current collectors. Yeah. We've thought about doing jelly roll and making sure that the open ends are parallel to the RF, B1 RF penetration. We haven't tried that experiment yet.
Cool, thank you.
Yeah, thank you.
Hello. I have a question about, like, in your system, will it be very beneficial to go to high fields? Could you comment on that?
Yeah, we tend not to go to high fields specifically for the paramagnetic materials because the paramagnetic broadening scales positively with field. In the case of the lithium plating studies, there's not as much paramagnetism there, but we already have really good chemical shift separation. So we rely on the wide bore spectrometer to be able to do the imaging and the diffusion sequences. So I don't think, at least at my lab, I don't have an opportunity to go beyond the field strength we're using.
It's great to hear that there's a race for lower fields for those of us who have some really low field magnets anyway for paramagnetism.
That's right.
I'm going to take the opportunity to ask. So capacity fade, of course, in batteries is the big deal. And so here, what I was really intrigued about, kind of being out of it for a few years, is this ability to see this sharing of electron density between the iron and the lithium. So does this give you some hints towards capacity fade, or is that too preliminary to comment on?
It might. In the iron case, we haven't done those studies, but for silicon anodes, for example, we've gone to 200 cycles to try and look at phase changes at long cycling. There you give up the paramagnetic interaction, so it's a bit of a different question, but certainly we're aiming to get to longer cycle lives.
Got so many different lithium chemical shifts and shieldings,
Yeah.
and then, you know, with the calculation possibility,
that's
maybe
right.
you've got a hint.
That's
So
right.
that's exciting.
Yeah.
First
great.
time maybe that we could see that.
Yeah.
Any other last questions for Jillian? If not, let's give her a hand for a spectacular talk. So cool, so cool. Okay, let's see. Next is, we've got Rick Dorn from Iowa State.
All right, thank you for having me here. I'm very excited to share some of our work with you guys. So before I start, I'd really like to acknowledge all the people who have participated in this work, because this could not have been done without them. So at Iowa State and Ames Lab, my PI, Professor Aaron Rossini, and our colleague, Dr. Alexander Patterson, who is now at the NMR fam. Then our catalysis collaborators at the University of Wisconsin-Madison, Professor Yves Hermans, and Doctors Melissa Sendages and Leslie Marks. And then some of the folks at the High Field Lab, and in particular, Doctors Jae-Hung Gung, Ivan Hung, Peter Gorkov, and Colette Chu. And I'd also like to thank the National Science Foundation for funding this work. So when you look at our nuclear magnetic resonance periodic table, one of the first things that we noticed is that about 73% of the NMR active nuclei have a spin of greater than 1/2, meaning that they are quadrupolar. And in addition, majority of these quadrupolar nuclei have a half integer spin. Now, when we look at many materials of interest, such as nanomaterials, oxide glasses, heterogeneous catalysts, and even pharmaceuticals, what we see is that many of these systems contain many quadrupolar nuclei. Therefore, there is great interest in the development of heteronuclear correlation experiments that can probe the spatial connectivity between quadrupolar spins. Now, these type of experiments have been done before, and the kind of most simple example is doing a JHMQC, which was demonstrated by Masio and Gong in 2005, where they did this for aluminum and oxygen. And this is kind of the more simplest case because no radio frequency pulses are required, so this is directly analogous to your spin 1/2 system. However, these require generally relatively large scalar couplings and transverse relaxation constants that are greater than the inverse of the J coupling for optimal efficiency. And as I'll show you today, we are interested in boron and oxygen, and these J couplings are very small. So therefore, we want to utilize the dipolar interaction. Now, people have shown that you can do cross-polarization between half integer quadrupolar nuclei. However, this is going to be highly sample and site dependent, and you might not observe some expected correlations. Now, for over a few decades, there have been groups applying dipolar recoupling to a half integer quadrupolar nuclei to obtain these heteronuclear correlation experiments, but this has been primarily limited to 1D reador type spectra, such as these dipolar dephasing curves, or just 1D filtered NMR experiments. And to the best of our knowledge, there have only been 2 reports of applying dipolar recoupling to a half integer quadrupolar spin to obtain these heteronuclear correlation experiments. And this has all been led by the group of Feng Deng, where they first did this for sodium and aluminum, and then very recently showed this for boron and aluminum. So today, I'm going to show you about our interest in doing this for boron and oxygen, and in particular, performing boron-oxygen restore and DHMQC experiments. And here, our recoupling sequence of choice is just simple rotational echo double resonance recoupling, where we are going to be using central transition selective pi pulses applied either to the boron or the oxygen spins. And we were motivated to perform these type of experiments because, as I'll show you towards the end of my talk, we can really utilize them to further determine structure within these boron oxide-based heterogeneous catalysts. So we first perform boron oxygen restore experiments to determine whether we can apply the recoupling to the boron or oxygen spins to reintroduce the dipole interaction under magic angle spinning. So as you can see here, here are some restore spectra with recoupling applied either to the boron spins in orange, or the green is the oxygen spins. When you apply recoupling to boron, you get a significant amount more signal dephasing. However, the dephasing curve tends towards zero at longer durations of recoupling. And this is because it's much more sensitive to fluctuations in the magic angle spinning frequency when you apply the recoupling to the observed spins. You'll also see that there's a lot more air at the end of these curves for boron recoupling, and that is because the T2 is also significantly shorter when you apply recoupling to the observed spin, which is not too surprising. Nevertheless, we can numerically simulate these experimental curves, and by scaling the extent of dephasing to match what we observe experimentally, we can estimate the oxygen enrichment level. And this is because the overall extent of dephasing is going to be dependent on how many oxygen atoms are attached to boron with the 17O isotope. And what you can see is that we get very good agreement with that determined from solution NMR spectroscopy. Now we could also estimate the oxygen enrichment level through a boron-oxygen J-resolved experiment with using central transition selective inversion pulses applied to oxygen. But this is much more time consuming because of the short boron T2 and the small J coupling of about 35 Hertz. We then recorded 2D boron oxygen DHMQ-C spectra. And here are two examples of 30% labeled boric acid at 18.8 Tesla with the recoupling either on the boron channel or the oxygen channel. And these spectra took about 40 minutes to acquire. We also did this for benzene diboronic acid that was 10% oxygen enriched at a lower field of 14.1 Tesla. And these spectra took about 4 hours to acquire. Now, the reason why a lot of these spectra actually took so long to acquire is because the boron T1 is actually on the order of about 10 to 20 seconds. Now, we could perform these HMQC experiments utilizing the scalar coupling, like Massio and Gahn showed. However, this requires significantly longer acquisition times because the boron T2 is so short, and the scalar coupling is about 2 orders of magnitude smaller than the dipolar coupling. We then determined the boron-oxygen DHMQC efficiencies by comparing a 1D HMQC to that of a boron spin echo, where we kept the echo time to match that of our recoupling time to normalize for transverse relaxation. What we can see for boric acid that is 30% oxygen labeled, we're getting efficiencies of around 6%, and for benzene diboronic acid, this drops to around 2% because it's only 10% oxygen labeled. Now, what is important here is that you see that the overall efficiency doesn't really change too much whether you apply the recoupling on the boron or the oxygen channel, thus demonstrating the general applicability of these type of experiments for many different spin systems. And the choice of recoupling is likely going to be sample dependent. We lastly numerically investigated the effects that the quadrupolar coupling constant for both boron and oxygen and the magic angle spinning frequency have on these DHMQC efficiencies. Well, you can see that it is generally robust to both the quadrupolar coupling constants and the MAS frequency, which again further demonstrates the general applicability of these type of experiments for many different spin systems. So now that we have these boron-oxygen experiments on hand, we actually want to utilize them to further determine structure within materials of interest. So the first system that we looked at was this oxygen-labeled sodium borate glass that was made by Dr. Alexander Patterson. So this 2D experiment was recorded at 18.8 Tesla in just under 1 day. And we estimate that this oxygen labeling is around 20%. So what we can see is we can clearly resolve the 3 and the 4 oxide. And if you look at the oxygen projection over the BO3 group, you can see that it correlates to 2 NMR signals previously assigned to bridging oxygen atoms shown in green and non-bridging oxygen atoms shown in blue. Now, when you look at the projection over BO4, what you can see is that it correlates to the expected bridging oxygen atoms, but it shows very intense correlations to the oxygen NMR signal previously assigned to a non-bridging oxygen. Now, this is intriguing because one would not expect that a BO4 unit would have a non-bridging oxygen, because then the formal net charge would be -2. So to further investigate this, we recorded a 2D boron-oxygen double quantum, single quantum homonuclear correlation spectrum. And what we see is that there are very intense BO4 correlations, suggesting that this motif must be abundant within this glass. And I want to point out that very similar abundant motifs were observed in this borosilicate glass from Matthias Eden's group in 2018. We then also performed density functional theory calculations on crystalline borate samples with known crystal structures. And what we see is that on average, an oxygen that bridges between two BO4s exhibits a lower isotropic chemical shift than an oxygen atom that bridges between a BO3 and a BO4 or two BO3s. So therefore, we are assigning this kind of unexpected correlation to an oxygen atom that is bridging between two BO4 units. Now, I do also want to share this. Just very recently recorded a 1D oxygen NMR spectrum at 35 Tesla using the SCH at the high field lab. And what we can see is that we almost can start to resolve out this oxygen atom that is bridging between two BO4s from the non-bridging oxygen, where they are completely overlapped at 18.8 Tesla. Now, the next system that I'm going to show you is what really motivated us to perform these experiments. And this is looking at these boron-based oxidative dehydrogenation catalysts. So in 2016, the group of E. Fermans demonstrated that bulk hexagonal boron nitride is highly selective for the oxidative dehydrogenation of propane to propylene, and that it significantly outperforms the previous state-of-the-art catalyst, which was vanadium oxide supported on silica. We can see there's very minimal over-oxidation with boron nitride. Now, we have collaborated with Eve's group over the years, and in particular for boron nitride, what we have been able to show is that under reaction conditions, there's this amorphous boron oxide phase that forms, and it actually directly grows off of the edges of the boron nitride framework. And it is this boron oxide hydroxide phase that are the catalytically active sites for this reaction. So with this knowledge, we were able to recently rationally design and develop this new catalyst, which is boron supported on oxidized activated carbon, and it exhibits ultra-high boron weight loadings of about 28%. And what we see is that this boron on carbon catalyst exhibits almost identical selectivities to the new benchmark boron nitride catalyst, but it is more productive and overall cheaper to make. Now, from boron NMR spectroscopy, we were able to show that about 80 to 90% of the boron is completely clustered on this carbon surface. However, we don't have a good understanding of these borate species. And what I mean, whether we have linear borate groups, if we have borates within a ring, and the relative population of hydroxyl groups throughout this layer. So here we're going to utilize oxygen NMR, and in particular these boron oxygen experiments, to really build a complete picture of what this active site looks like. So we first recorded 1D oxygen NMR spectra from 9.4 Tesla all the way up to 35 Tesla using the 36 Tesla series connected hybrid magnet at the high field laboratory. Now, we were able to confirm all of our oxygen NMR signals from this very beautiful MQMAS at 18.8 Tesla that Dr. Ivan Hung recorded. And what we see is that there are two main groups of signals, which correspond to the hydroxyl groups and the bridging oxygen atoms. Now, what is really interesting, you can see there's clearly two unique bridging oxygen NMR signals that have very different quadrupolar asymmetry parameters. Now, there's some really nice work from Ray Dupree's group in 2009, where they studied boron oxide with oxygen-17 MQMAS and DOR experiments, and also used quantum chemical calculations. And what they're able to show is that the low eta site corresponds to an bridging oxygen within a linear borate group, whereas the high eta site corresponds to an oxygen atom bridging within a ring. So this shows that this catalyst contains both linear and ring type borate species. We then also performed boron oxygen HMQC experiments to kind of confirm our assignment of this low frequency site to hydroxyl groups. Now, what is important is that as we increase our recoupling time and go up quite far, we basically get back out our direct excitation spectrum. And this is important because it is showing that these hydroxyl groups are kind of homogeneously distributed throughout this boron oxide layer, and they are not primarily limited to the surface. So now with complete oxygen signal assignment on hand, what we can see from our ultra high field oxygen NMR spectrum is that about 50% of the oxygen are hydroxyl groups. So this is showing that this oxide layer is extremely hydroxyl dense. Also see that there's about a 60-40 ratio of ring type to linear borate species, showing that both are also very abundant. We lastly then recorded these 2D boron oxygen HMQC spectra, and here's one at 18.8 Tesla, and this took about 15.5 hours to acquire, where we start to get relatively good resolution where we can resolve the hydroxyl groups from the bridging oxygen atoms. Now, we very recently recorded this 2D NMR spectrum at 35 Tesla, And this only took about 4 hours to acquire. And we are kind of looking at a surface here of only about 20% enriched oxygen. So this is quite impressive. And what you can see, we get very good resolution, and we can actually resolve the linear from ring type bridging oxygen to atoms in this HMQC. So now we can really start to build a complete picture of molecular structure because we know that this is extremely hydroxyl dense and there are a lot of ring type and linear borate species. Now from the HMQC, we can see that the most intense boron NMR signal, which corresponds to about 80 to 90% of the boron, correlates to all of the oxygen NMR signals, the hydroxyl groups and the both type of bridging oxygen atoms. So it's kind of confirming that they're homogeneously distributed throughout this layer. Now, what is also interesting is that if you look at these lower frequency boron NMR signals, these are presumably coming from or grafting to the carbon surface. They primarily correlate to the linear type bridging oxygen atoms, suggesting that this layer is kind of linearly grafted to the carbon support, which is also probably not too surprising when you try to draw what the structure looks like. So today I showed you of how we are using rotational echo double resonance recoupling with central transition selective pi pulses to enable the acquisition of these dipolar-based Restor and HMQC type experiments. And we anticipate that this should be generally applicable to many different types of spin systems. I lastly then showed you how we can actually utilize these heteronuclear correlation experiments to really further determine structure within materials of interest, such as this sodium borate glass and this boron oxidative dehydrogenation catalyst. And performing these experiments at ultra high field is going to be extremely beneficial because you'll get central transition line narrowing in both dimensions. And with that, I'd like to thank you all for your attention and again, acknowledge the people who have participated in this work.
Thanks, Rick. So questions for Rick, and again, encourage students and postdocs first.
Hi, thank you for the talk. I was just wondering, are there any different considerations for optimizing the quadrupolar to quadrupolar DHMQCs versus like a spin half to quadrupolar?
I mean, you could change your choice of recoupling. So we really just investigated Redor. I mean, there's a couple other things you could do involved in it. One of the things that we didn't actually do is apply like population transfer during the recoupling. We are mostly probe limited in that sense because these are quite weird tuning ranges. Does that help answer your question?
A little bit. Thank you.
I can add, they're generally robust. So, I mean, as long as you have your RF calibrated roughly around the matching condition, the experiment works just fine.
What's the sample that you tune up on to set up for that experiment? Or are you optimizing on?
Yeah, we started with boric acid because it's super easy to oxygen enrich and it's very cheap. Yeah.
Hey, nice talk, Rick. Have you also tried oxygen 17 excitation type experiments? What's the O17 T1 like in some of those samples?
So doing the experiment but observing oxygen?
Right.
Yes, I have done that. It's not as sensitive, just detecting a lower gamma nucleus.
Right.
But what was interesting is then if you do something like that, then you can actually start to implement these like double quantum satellite transition based experiments like Jaehong has shown.
Right.
But those are generally much less sensitive.
But what is the T1 of oxygen? Have you tried measuring?
Yeah,
the T1?
actually quite long.
Oh, really? Okay.
Yeah, like so in that catalyst, the oxygen T1 is actually like 30 seconds.
Oh, wow.
So
Okay.
yeah, I don't know why.
Interesting. Okay, thanks.
Yep.
Other questions? Otherwise, I'll take the opportunity to ask. So, you know, the hydroxide density seems really pretty prominent in
Yep.
this system, and that's the one that's grown on the activated carbon. Do you think it's scavenging hydrogen in the growth from the carbon somehow? Or, you know,
Probably not too much. So I do think so. These samples will likely actually lose hydroxyl groups under reaction conditions.
Oh.
So because they do the reaction at 500 degrees Celsius. So I'd imagine some of these are going to be removed. Water is a byproduct in the catalysis too, so it's probably going to get sucked off a little bit. The surface of the carbon, they acid treat it first to form all these different functional groups. So it very well could be coming from there as well.
but the catalysis that you showed that was comparable, so that was only a first cycle as opposed to
They've showed that you can do that. I don't know if they've ran multiple cycles, but they've done it for like 24 to 48 hours on stream, and it is just completely flat. They all have these very slight induction periods, but the boron and carbon has a much smaller induction period because you already have the active phase basically there. Whereas like the boron nitride, you have to grow the active phase off the edges. So your induction period is like 12 to 20 hours.
Okay. Yeah, thanks.
Yep.
Well, with that, any other last questions? If not, let's thank Rick for a tremendous work. So next, I'm delighted to introduce Danielle Pardon Alvarez from the Weizmann, who's coming to us from the Weizmann Institute.
Okay. So can you see my screen? So I'm very happy to be here and to have the opportunity to show you some of the work that we've been doing in our lab. So the title of my talk is Monitoring T1E with Paramagnetic Relaxation Enhancement and what we can learn from it. So maybe the main question that motivated this work was we wanted really to understand how the magnetic resonance properties of our samples change when we introduce paramagnetic species. And specifically what happens as a function of the concentration when we go from highly diluted cases where the paramagnetic species are just minor dopants all the way to highly paramagnetic samples where they are major constituent of the chemical structure. And in NMR, we often introduce paramagnetic species to reduce the relaxation times. But sometimes we have to pay a price for this, which is that the lines becomes broader. And sometimes it even gets to the point that we have signal quenching. And by signal quenching, I mean that there will be some portion of this NMR active nuclei that we cannot observe just because of their proximity to the paramagnetic center. And this is something that is well known and has been quantified. So I'm showing you here two examples, one from our group where we looked at the signal intensity as a function of the manganese content, and the other one from the group of Johan Schmidt of the Gunne, where they looked at the same in terms of the gadolinium content. And now the interesting part here is that if we would extrapolate this curve, one would predict that it would be possible to do NMR and high paramagnetic content samples. But of course, we know this is not true. We just saw Gillian's talk where she was showing us lithium-7 spectra, which of lithium-7 nuclei that were sitting nearest neighbors to iron, paramagnetic iron. So the fact that she was able to observe the spectrum means that they are actually able to see all the nuclei in the sample. So there's no quenching at all. And here I'm showing you just a few other examples from the group of Claire Gray. And also, this is also true for some examples where the paramagnetic centers were in lower concentration. So they were able to observe a nuclei sitting next to paramagnetic center at low concentration. So what's going on here was the question that we were asking us. And obviously the answer has to be that the properties of the electron spins on the right side and the left side of this figure must be different. And this is the question that I want to investigate more thorough in this talk. And so for that, we prepared a series of samples of compositions, lithium, magnesium, manganese phosphate. And we chose this system because here we are able to substitute the diamagnetic magnesium by paramagnetic manganese from 0 to 100% without altering the crystallographic structure as we verified with X-ray diffraction. And another reason we chose this system is that it has a couple of NMR-friendly nuclei. So here I'm showing you the lithium-6 NMR spectrum for some various concentrations. And what we observe is that at the low concentration regime, we have a single peak as expected from the crystal structure, which is quite narrow. And as we increase the content of manganese, this peak becomes broader and broader. But then we reach a point where it actually starts becoming sharper again. And at this point, we're able to observe multiple sites. And these multiple sites are due to differential Fermi contact shifts, but I don't want to go into that part of the story today. Instead, I want to show you something else. So we quantified the signal intensities for all these samples, taking into account a number of scans, moles of lithium-6 and so on. And we obtained this interesting figure of the signal intensity versus the content of manganese. So what we observed was that at the low concentrations, the signal intensity was dropping as we were expecting because we have signal quenching. But there is actually a point where this trend reverts, and then further increasing the manganese content actually allowed us to see more lithium nuclei again in the sample. And at the very high concentration, we were able to virtually see all lithium again, like Jillian, for example. And so what this figure is telling us is that the increase in paramagnetic content must be affecting properties of the electronic spins. So as we have more and more manganese, the electron couplings become stronger. And what this will cause is that the electron relaxation times of the electron will change. So ideally, we would like to probe this. And the easiest, the best way would be to do the EPR measurements. But measuring electron relaxation times with EPR at these high concentrations at field and temperatures of interest is like extremely challenging or even impossible. So what we decided to do is to map this electron relaxation with the nuclear relaxation instead. And I'm going to show you how this can be done very easily. And I should mention this approach has been already done and reported by the group of Jeroniak. So paramagnetic relaxation enhancement is the nuclear relaxation due to the presence of paramagnetic species. And I'm showing you here the equations for T1 and T2. So the longitudinal relaxation rate is equal to the strength of the interaction squared. So the relevant interaction here is the through-space Dipole coupling between electron and nucleus times the spectral density at the Larmor frequency of the nucleus. Now, the interesting part here is that because this is a rigid solid, there are no structural reorientations that could cause relaxation. So instead, the source of the fluctuating fields that cause relaxation of the nuclei are the random fluctuations of the magnetic moment of the electron spins themselves. So the electron spins are fluctuating because of their own relaxation, and this is felt by the nuclei as a fluctuating of the interaction. And the correlation time that describes this fluctuation is the electron relaxation time, T1e. So I'm writing here tau 1e because there are also coherent effects that are not strictly speaking relaxation that we know that can contribute, but anyhow. And then the T2 relaxation time has an additional term, which is the spectral proportional to the spectral density at zero frequency. Now, if we plot these two equations of the relaxation versus the correlation time, we get this very famous figure of NMR relaxation, where T1 passes through a minimum, while T2 keeps decreasing with increasing correlation time, so with slower motions. So now, how would this curve look like if we increase the strength of the Dipole coupling? Well, the curve will look exactly the same, just shifted down, so to shorter relaxation times. And now I want to drag your attention to the fact that actually the ratio of T1 over T2 has not changed between the two cases. And it only depends on the correlation time, which in our case is the electron relaxation time. So other way around, we can use this fact, and just if we know the ratio of T1 over T2, we can obtain the electron relaxation time. And this can be shown mathematically just by dividing one equation over the other, and here we obtain that, in fact, that T1e is proportional to the ratio of T1 over T2, and the only other unknown parameter is the Larmor frequency, which is actually a known parameter. So with this tool in hand, then we went back to the manganese series and re-evaluated our results. So here I'm showing you the lithium-6 relaxation times as a function of the concentration. And in the low concentration regime, they follow nicely the expected behavior shown here in dashed lines, which is that the relaxation time decreases with the inverse squares of the concentration of paramagnetic species. But then at some point, we start deviating from this expected behavior. So you can see that T2 drops slower than we would expect. And then at some point, it actually even starts increasing, so the T2 is getting longer with increasing paramagnetic concentration, which is very counterintuitive at the beginning. And if we look now at the ratio of T1 over T2, we get this figure here. So at the low concentration, the ratio is largest and is more or less constant for a while, and then it starts dropping quickly. And using the equation that I just showed you before, we can estimate the electron relaxation time. So for the longest cases, we are somewhere around 0.8 microseconds, and then we drop quickly into the nanosecond regime, and then until we reach here the extreme narrowing regime. So we wanted to know if these estimations are more or less correct. So what we did is we were able to do some EPR relaxation measurements at high fields for the lowest concentrated sample for a temperature up to 100 Kelvin. And at 100 Kelvin, we had like a T1E of about 2 microseconds. If we extrapolate it to room temperature, which is where we did the NMR, we see that we are at least more or less in the right order of magnitude. And Ilya Kuprov told us today in the morning that in solid state, relaxation being in the right order of magnitude is the best we can get. So we're happy about this. So one more thing that we can do is actually we can fit this curve and we obtain that the electron relaxation time is proportional to the mean distance between manganese center to the power of 6, which is a good indication that the reason for this decay in the electron relaxation time is the through space electron dipole coupling. So to summarize this and connect it to the quenching story, so at the low concentration regime, we have very long electron relaxation time. So in the BPP model, it puts us on the very right, far right side of the figure, meaning that nuclei in close proximity to the paramagnetic center will have an extremely short T2. This is equivalent to the quenching radius around each paramagnetic center being very large. Now we start increasing the concentration. At the beginning, we don't affect the electron relaxation time, but we increase the number of quenching spheres. So the signal intensity drops, which is what we were observing. But then we enter this regime where the relaxation time starts becoming shorter. And if we go back to the BPP model, it's like moving from the right to the left. So for a fixed distance, the T2 of a given nucleus will start increasing. And this is equivalent to the quenching radius becoming smaller and smaller. And at some point, this shrinking is more important than the increase in the number of spheres. And at this point is when this is the point where the quenching inverts. And then at some point, the radius of these spheres is so small, and this is the reason why we are able to observe nuclei in nearest neighbors to the paramagnetic center. Okay, so for the rest of the talk, I want to switch a little bit the topic. So I'm gonna try to show you how this T1 over T2 ratio can also be useful to understand DMP enhancements. And before I go into that, I'm gonna introduce you quickly how we do DMP in our lab, because it's a bit different from most of the solid state DMP experiments that are being done. And so what we do is we don't use exogenous nitroxide radicals. Instead, we dope our samples with paramagnetic metal ions, which then upon microwave irradiation act as polarizing agent and are able to polarize the nuclei in the sample. Now, the main difference maybe compared to the exogenous cases that our samples are inorganic, unprotonated solids. So spin diffusion is going to be very smaller or even not present at all. So the first question that we asked ourselves is, how far can we polarize in the sample, like from one electron inside into the bulk of the sample? And to answer that, we have to look at the relevant DMP mechanism. In our cases, it's mostly always the solid effect. So the solid effect we can describe with a two-spin system of one electron coupled to one nucleus. And the idea in the DMP solid effect mechanism is to irradiate in one of the formally forbidden, either double quantum or zero quantum transition. And if we do so, if we are able to equalize the population of these two energy levels, we create a large population difference between the NMR transitions, which is what gives us the enhancement. So now, because this is a formally forbidden transition, the efficiency of this irradiation actually scales with the strength of the dipole coupling over the nuclear Larmor frequency, meaning that nuclei that are farther away will have a less efficient, it will be less efficient for nuclei the farther away you get. Then at the same time, we have to consider what is trying to counteract our effort to saturate this transition, and it is the relaxation. So now here comes the fun part, because these are rigid solids where there are not many relaxation mechanisms present. The main source of relaxation is actually the metal ion that we introduce for polarizing. So it has this double function. It gives us the polarization and it inhibits us from getting more polarization. So, and here again, the same story is true. Like the further away we are from the polarizing agent, the weaker the interaction, the longer the relaxation time, the more time we have to get the enhancement to these nuclei. So if we take all these considerations into account and we compute or we calculate the DMP enhancement, which is just proportional to the saturation efficiency of this transition, we actually find that the DMP enhancement is independent of the strength of the dipole coupling. And this result has huge impact for us because it means that the enhancement is independent of the distance. So we can get homogeneous enhancement throughout the bulk of the entire sample. And this is the reason why this method works so good and why we are able to get DMP enhancement on very low sensitivity nuclei without the requirement of spin diffusion. I'm going to show you a few experimental examples. So this is iron-doped lithium titanium oxide. And here you can see the DMP enhancement for lithium-6 and for oxygen-17 at natural abundance versus the iron concentration. And one interesting thing that we observed is that the enhancement is actually over a large range of concentration independent of the concentration of iron. And the reason for this is just what I just told you before, that the DMP enhancement is independent of the distance. So if we increase the concentration of iron, of polarizing agent, we are merely reducing the distance, which will give us faster buildup times, but not higher enhancements. And of course, this condition fails at some point. So it fails in the low concentration regime because at this point, the intrinsic relaxation mechanism of the nucleus starts kicking in. So the condition, I forgot to mention, the condition for this distance independence is that the main relaxation mechanism or the dominating relaxation mechanism is the PRE, the paramagnetic relaxation enhancement. And in the high concentration regime, we also start deviating from this behavior at some point. And this is because the electron-electron coupling starts becoming stronger. And as I showed you before, the electron relaxation time starts dropping. So now we wanted to see if we can say something more quantitative about this change in T1E using the T1 over T2 ratio that I showed in the first part of the talk. So for that, we took one of these samples, so this one, looked at the lithium-6 enhancement as a function of the temperature from 100 Kelvin all the way up to room temperature. And at the same time, at each point, we were measuring the T1 and the T2 relaxation times. Now, if we take the equation to get the T1E from this ratio, we actually observe a linear dependence of the DMP enhancement with this electron relaxation time. And maybe the main message I want to pass with this figure here on the right is that we can just very easily measure T1 and T2 and with this we get a nice idea if a new polarizing agent or a new material doped with a metal ion will be suitable for DMP. So just by measuring T1 and T2. And with this, I would like to conclude. So I hope I was able to show you today that it's really useful to measure both T1 and T2 relaxation times because we can learn a lot about our magnetic resonance properties of our system, both in terms of signal broadening and quenching, and also in terms of metal ions DMP. Maybe the next step that we would like to do is if we would be able to get large DMP enhancement of signals that are Fermi contact shifted. This would give us specific information about the coordination environment of our dopants. But the difficulty here is that for DNP, we need long electron relaxation times in order to be able to saturate the forbidden transitions. But if this is the case, then the quenching sphere will be large, and we shouldn't be able to observe neighbors of the paramagnetic species. But that we are trying now, and hopefully some of them work. So with that, I would like to thank all my great colleagues from the group, especially my PI, Michal Leskes, and I also would like to thank Hans van Tol, who did the high field EPR T1E measurements. And of course, you all for your attention.
So questions for Daniel?
Hi, really enjoyed your talk. I just had sort of a more general question about your enhancements you're seeing in your materials. And your enhancements are very good, very, very good. And when I've been trying myself to do something like manganese in the endogenous radicals, I'm not seeing the concentration dependence. I'm also seeing very, very poor enhancements. So I'm just wondering, have you had any luck with getting good enhancements in amorphous materials? Because everything you're showing is very crystalline.
Yeah, so thanks. So yeah, I'm aware of your work. I'm aware of your work, and we're actually also working on looking at exactly this question, like why we have much better enhancement in crystalline materials over amorphous materials. So what we did is we prepared samples of analog composition, so some silicate glass and silicate crystals, and just look at the DMP enhancement, and we were like order of magnitude difference, from 10 to 100, something like that. And so we've been looking at it, like scratching our heads, like why is this? And kind of the conclusion that we get to is like it's a couple of different things contributing. One of them is just the electron relaxation time seems to be shorter in the glasses, and it's always I don't know why, but it is the case. And so there we have like a factor 3 or 4, and then we have found other things, and I hope we publish this soon. So we have found like a couple of things that contribute to this.
Cool. Thanks very much.
Thank you.
Hi, nice talk. I have a kind of a basic question. Is there kind of an intuitive way to understand why the electron relaxation times get longer once you increase the concentration and the coupling increases?
Now the electron relaxation time gets shorter due to electron-electron dipole coupling.
It gets shorter. Sorry, yeah.
Yeah. So the relaxation mechanism is the electron-electron coupling, and the higher the concentration, the stronger the coupling.
Okay, thanks.
Okay.
It's still a little counterintuitive, though, it seems, but maybe, yeah, please.
I have maybe a kind of naive question about the DNP and paramagnetic materials, but did you say that if you have more dopant, then your DNP enhancement like reduces, or doesn't like scale with the amount of like paramagnetic centers, right?
Sorry, I have a bit of an echo. Can you repeat?
But basically, like my question is, if you have a paramagnetic material entirely, does that help you with the like endogenous DNP enhancement? Or
then no chance. Then the electron relaxation time is just too short, and we're not able to saturate this transition.
Okay,
so
that interaction dominates, and then it.
Yeah. So
okay.
Yeah.
Thank you.
So the first thing we have to look at is long electron relaxation times. Otherwise, no chance. Yeah.
I know we're low on time, but could I just ask one brief one? So isn't there anisotropy in the electron nuclear dipolar interaction depending on the crystalline solid? Or do you assume it's isotropic in all?
No, there is, but so where do you want, like?
Yeah, could that be used as a design parameter? Is that anisotropy?
No, so I mean, kind of what I showed you was that for this case, for example, the DMP enhancement is independent of the strength of the dipolar coupling. So it's either if it's weaker because it's farther away, or because it's just like an angle to the magnetic field that is not favorable. It doesn't really matter. So I think the enhancement, I think the enhancement is going to be homogeneous throughout the sample, and this is what we observe. We see no changes in the line shape from microwave on to microwave off. So we see changes versus build-up time, because first we build up the magnetization of nuclei that are closer, which are broader, but this happens in both cases, with enhancement and without. Yeah.
With that, let's thank Daniel.
Thank you.
For some excellent work. Our next speaker is Emma Latcham, I believe, from University of Cambridge.
Sorry. Right. Yeah, thank you very much for coming to my talk today. I'm really excited to be here. This is my first ever in-person conference. I'm a second-year PhD student in the fourth group, and the sort of overarching aim of the group is to look into climate change mitigation strategies. My research is focused on looking at capacity fade in redox flow batteries. I sort of do this using solid-state NMR and also in-situ studies with the operating battery. And today I'm just going to focus on my in-situ studies. So the motivations for the project are basically, obviously we all know we're in a climate crisis right now, and a significant proportion of the CO2 emissions come from electricity generation. And you can see in this graph here that shows the percentage contributions to the global electricity supply, that the actual contribution from renewable energy sources hasn't massively increased over the last few years, although the overall supply has increased. And part of the reason for this is just due to the intermittent nature of energy coming from these renewable sources. So you can see on the bottom trace here, a typical grid demand. And if you compare this from a typical energy output from something like solar supply, you can see it's not particularly well matched. And the situation gets worse when you look at things like wind. So if you imagine we were solely relying on wind energy, we just wouldn't have a reliable energy source. So in order to actually integrate a higher percentage of these sort of energy sources, we need to use some sort of balancing capacity. So often this is actually done using things like natural gas, but obviously we want to move away from greenhouse gas emitting solutions. So energy storage is a really good technology that we want to be trying to integrate onto the grid. So why isn't this really done much so far? There isn't much storage on the electricity grid currently. So most of the energy that's generated is instantaneously distributed to be used. So if you look at a sort of conventional battery, such as a lithium-ion battery, we have excellent capacity, we have excellent energy storage density, and we have fast discharging, which is great. However, they're quite expensive. So it would be uneconomic to actually integrate loads of lithium-ion batteries onto the grid. And part of the reason for this is because a lot of the energy, or the energy is stored sort of completely contained within the battery, so at the electrode. So the batteries that I'm really interested in looking at, redox flow batteries, the difference here is that you have the energy stored in two liquid electrolytes. They're actually external to the battery. And these liquid electrolytes can then be pumped into an electrochemical cell where the charging and discharging takes place. So you can sort of imagine that if you want to increase the capacity of this battery, it's quite simple. You just have to increase the actual volume of the electrolyte. And this is quite beneficial because it just means it's really ideal for scaling the actual capacity that you want to have on a grid level energy storage sort of system. So another benefit of these batteries is the fact that we don't have the changes at the electrode, so we have an inert electrode, and this means potentially they're sort of more economic over a longer period of time. This is just a little bit more detailed diagram of a redox flow battery. So you basically have, there we go. So we have a porous electrode, which is just a carbon electrode, and this is just provides like an active area for the redox reactions to take place. We then have peristaltic pumps, which pump the electrolytes into the battery interface where they are charged and discharged. And then we have an ion selective membrane. And the idea here is this just allows the transport of charge balancing species, so you can maintain electroneutrality. However, we want to have separation of the two solutions, because in solution we have redox couples. So the system I'm looking on is based on an organic redox couple. And the benefit with using organic materials is basically they can potentially be manufactured really cheaply. They're also potentially a lot lower, less toxic than other technologies such as vanadium-based flow batteries. And these are sort of two things we really want to move towards a sustainable energy future. So this system that I'm presenting here is one that was reported by Lin et al. It's a really good model system for aqueous organic flow batteries. And this is just sort of what I've been basing my initial studies on. So my actual project is focused mainly on the separator membrane, so I'll just talk about this in a bit more detail. So the typical separator membrane that's used in industry is a Nafion membrane. So this is a cation exchange membrane that's designed to conduct cations, but basically repel negatively charged ions, such as the quinone and also the ferrocyanide. So these are the molecules that store the actual energy. And this basically works by, we lose this proton here when we're in a basic solution. So we have a negatively charged sulfonate group. So what we want is we want the membrane to be conductive so that we can maintain electroneutrality, but we also want it to be selective because if we have crossover of this redox active material, we basically just lose capacity in the battery. So yeah, this is termed as a crossover. So how am I studying this? Basically, this is sort of the setup that I've been using for, I use this for just some initial simple studies. So in the feed side, we just have the quinone, which is the electrolyte of interest. And then in the permeate side, we just have the solution that the quinone is dissolved in. And this is flowing through an NMR spectrometer where we're collecting a proton spectrum that's averaged over 10 minutes. So this is just using a pseudo 2D experiment using a simple pulsar sequence. So the way we're actually doing this is using a commercial Bruker Insight MR flow tube. So this is a part of a collaboration with Bruker, with Matteo Pinentri, who's lent us this equipment. And this is really useful because, as you can see here, it sort of looks very similar to a normal 5mm glass NMR tube. And then the top is, it basically means that we can put this straight into a standard sort of 5mm NMR probe. So we can use this in pretty much any spectrometer in the department, which is great. And then just looking in a bit more detail, hopefully you can see there's sort of a orange tube that goes into the bottom of the glass tube. And this is where the electrolyte comes in. And then out through pressure, there's a sort of hole at the top, which connects to an outlet. So this just means that we can continuously collect data. So a lot of studies that look at crossover and permeability tend to do this ex situ. But the reason I want to do this in situ is many reasons, actually. So firstly, we have minimal system disturbance. So for this battery, it's actually meant to be operated in the absence of oxygen. So you can imagine doing ex situ samples can affect the functioning of the battery. And then same also, you just lose material and it just complicates things. We also have high temporal resolution that isn't possible with ex situ. And this means if we're looking for like more transient species, it's particularly useful. Here I've taken a spectrum every 10 minutes, but we can reduce this down to less than a minute if needed. Also, we have continuous regular data collection. So for example, at night, the department's closed, so you can't really be collecting data if you're doing this ex situ. And then the excellent thing about using NMR is we can actually differentiate between crossover and degradation. So I didn't mention this before, but the electrolytes can degrade into non-redox active materials. This also contributes to capacity fade. So later on in the studies, I want to look at how we can sort of differentiate the contributions to capacity fade. A lot of the studies that are done on crossover use sort of electrochemical techniques, and it's often hard to tell exactly where those electrons are going and determining what's contributing to the capacity fade. So this is just some of the actual data that I've been collecting, and these 3 resonances correspond to quinone that's passing through from the feed side into the permeate side. And you can basically see that over time we're getting a increase in the signal intensity, and also you might notice there's a shift to lower chemical shifts. This is related to intermolecular interactions at higher concentrations. But the main thing here to take away is the fact that we can basically see the increase in intensity. So we want to use this increased intensity to sort of measure the crossover rate. However, as we've got flow, it's slightly more complicated. So we have T1 relaxation effects to consider. As we're actually flowing the electrolyte into the magnet, if we flow too fast, we basically lose signal intensity because we're not getting back to equilibrium magnetization. However, there's a relatively simple solution to this. We can just use stopped flow experiments. And this is basically where we take a spectrum while flowing the electrolyte, and then again, when not flowing the electrolyte, and we just get a correction factor so that we can still obtain quantitative information. It's also important to consider this depends on the T1, so you have to make sure you're doing this for the correct T1 in that situation. So basically from this, we can obtain quantitative data about the increase in concentration of quinone over time in the other side of the cell. And from this, using Fick's law, we can basically just look at the increase in concentration of quinone. And as this is basically, it's just basically a permeability that's normalized by the area of the membrane and the membrane thickness. And we just use this to get a permeability value, which is a useful metric to sort of compare the performance of this electrolyte with different systems. However, this is sort of an experiment that's been done before, just looking at the permeabilities of different electrolytes. But I just want to think about how well does this actually predict the performance in a fully operating flow battery. And there's a few reasons why I think this could be different. For a start, when we are charging the quinone, we're actually changing the charge density. So we're going from a 2- into a 4- state. And you can imagine that as we're using a cation exchange membrane, you'd expect this to increase the repulsion and therefore potentially reduce crossover. However, there's also other additional transport mechanisms to consider. So we have migration, which is basically where the quinone itself could be used as the charge balancing species. So when you charge the battery, this could be a driving force to increase crossover. We also have things like electroosmosis, which basically is where the water gets dragged in with the ions. And then we also have electrochemical degradation that you wouldn't normally see in a normal diffusion experiment. And these are just a few examples that have been reported previously. So the setup that I used for looking at an actual fully operating battery is relatively similar to what I used previously. It's just this time I've basically added the ferrocyanide into the catholyte side of the battery. And this is basically just allowing us to charge and discharge the battery so we can see how this affects the performance. And this is just a photo of the actual setup that I used. So you can see here, these are 2 peristaltic pumps. And this is what pumps the electrolyte from the electrolyte reservoirs that are here. Sorry, it is a bit messy, but yeah, it's not easiest to see. And then this basically pumps the electrolyte into the electrochemical cell, which is connected to a potentiostat. And this basically allows us to control the voltage of the battery and also the current, and then measure the changes in current as well. And then once it's come out of the cell, it goes straight into the NMR spectrometer. So this is a photo of the full setup. And then we take a spectrum that's averaged over 10 minutes. And then this goes back to, oh, sorry, in this case, it's every 3 minutes. And then it goes back to the electrochemical, the reservoir. So I just wanted to talk through the sort of experiment that I used for this. Firstly, we have no charging. So you can see this, I haven't got the cell voltage here. And this is just to get a background permeability as we did before. Then we charge the battery, and the idea here is that we're now going to the 4- state, and then we hold the potential here for a while so that we can, the idea was to see if we can see a difference in the crossover rate at, when the battery is fully charged. And then at the end, we're just doing the opposite. We're discharging the battery and going back to the 4- state. So now you can see I've just added the change in quinone concentration, and that's shown in blue. And just, yeah, I've given a sort of a diagram in the corner here to sort of try and explain what's going on in each step. So at the start, we're just looking at quinone crossing over just as normal, and we're detecting it in the catholyte side. And from this, we can then calculate a permeability just as before. And then in the second part of the experiment, we are now charging to the 4- state. And at the start, you see we can get a permeability. Interestingly, this permeability is actually higher than we see when we are not charging the battery, which suggests that possibly there's migration could actually be driving additional crossover of the quinone here. And then we do also see this sudden drop in quinone signal, which we weren't expecting to see at all. So I've actually used proton A to actually quantify this, but all of the protons are lost, proton signal is lost. So it shows that we are, basically the quinone is going to some form that we can no longer detect by NMR, so possibly it's degrading. And this is something that hasn't previously been reported in the catholyte side of the battery. And then finally, when we discharge back to the 2- state, we can then get a permeability again that's sort of relatively similar to the initial permeability that we get, that possibly further supports that migration is driving crossover during the charging step. So just to conclude, we basically developed a method to characterize crossover in an operating redox flow battery. And this has just been done so far using a benchmark system. We've seen some evidence for the quinone degradation in the catholyte side, which previously hasn't been reported. I think this also shows the strength of using in situ NMR, because if we were using ex situ experiments during this, it would be harder to sort of understand where this signal loss had come from, depending on where you were sampling. And then we've also seen from the initial results that there is a relationship between the charging protocol and the crossover rates. I think this is really interesting because it means that there is the potential to sort of manage the protocol used for charging the battery, and therefore potentially manage the capacity fade that we actually see. But finally, the ultimate aim of the project is actually to look at a range of different membrane electrolyte combinations. And the idea here is that we want to basically see if we can unravel any sort of structure property relationships that govern crossover and ideally sort of design new and better membranes. So yeah, I would just like to thank everyone who's helped me on this project, particularly my supervisors, Dr. Alex Force and Professor Vasant Kumar, and everyone in the Force group, which is just shown in this photo here. And yeah, many other members from different groups in the department, including the Duo group and the Grey group. Yeah, and thank you very much for listening.
Thank you, Emma. Questions for Emma?
Hi, very nice talk. I was wondering if you're using any deuterated solvent in your flow cell because you need to maintain a frequency lock, because I saw those shifts and I was wondering if maybe it's just the instrument or if you actually, they're real shifts.
Yeah, I'm using the D2O as a solvent, but then I'm using potassium hydroxide, which isn't deuterated because it's just really expensive. So yeah, we do have protons from the potassium hydroxide and also the quinone itself. But yeah, the shift has actually been previously reported for other quinones. And that's sort of where I got the idea that it's to do with some sort of dimerization. But yeah, I think I do need to investigate it further, but it's just sort of an interesting side point, I guess.
Cool, thank you very much.
Thanks, it was a really lovely talk. I'm curious about the species, not the quinone, but the other species. Does it have a proton signature and do you watch it in the process as well?
Yeah, so it doesn't have any, we don't have any proton, well, actually that's not totally true. We do have some weird impurity there that we're not completely sure what it is, but it's very small. It doesn't have a proton signature, but it is quite complicated when we charge a battery because it goes to a paramagnetic species. So the entire chemical, the whole spectra shifts to higher ppm. So we have to sort of correct for this. And also, yeah, it complicates things because it reduces the T1 of the quinone. So this is something we have to account for in the quantification. In like my later experiments, I'm trying to work in a regime that's just completely quantitated by using like a slow enough flow rate. But yeah, it makes it a bit more complicated, yeah.
Right, lovely. Maybe if I can, a second question is, have you thought about using a diffusion experiment to study the actual crossover process?
Yeah, actually, we've thought about it. So the idea is for my solid state NMR studies, we actually look at the quinone in the membrane. And so far I've just been looking at absorption of the membrane and trying to quantify it. But one of the things we'd like to do is see if we can actually get a sort of in-membrane diffusivity, because then looking at the solution diffusion model, we could sort of get the permeability that we have from the in situ experiments and sort of compare that to the diffusivity and the absorption and see if it all sort of makes sense. But no, I haven't thought about that in situ yet. Yeah.
Lovely, thank you.
Thanks.
Do you see any change in the proton signal breadth for like the last example as you're charging and discharging, especially as you see like it goes basically to zero? Are you just getting some agglomeration and then it's basically the correlation time is matching the alarm frequency, so it's like invisible?
That's a good point. I do see the spectra gets broader as we charge because we're producing paramagnetic species, but for the potential hold, it's really weird. They just disappear very quickly, and I don't see any broadening. So yeah, I definitely need to investigate that further, but
sure.
Yeah.
Thank you.
Hi, very nice talk. So it's pretty intriguing that you lose this the signal when the battery is charged. I guess you don't see any degradation products. Could it be that the quinine like diffuses back through the membrane? Is that something you've considered instead of degradation?
The what? Sorry.
This anthraquinone, does it diffuse back to the membrane to the other side or something?
Yeah.
I mean, it's very uncommon that you don't see any degradation products in these organic molecules.
Yeah, I did think it was very strange. I thought, so no, we haven't seen any others. And what I want to do is look at like carbon NMR, see if, because maybe we've just, I don't know what's happened with the protons. I thought maybe it'd be useful to do carbon. I don't think it would be very strange to see crossover back into the other side, just because it's such a high, so much of a higher concentration on the other side. Yeah, I'm not completely sure. But I was thinking maybe something to do with paramagnetic species forming, maybe, that makes the protons hard to see, or yeah.
Yeah, cool, thanks.
Thanks.
Brief question.
Just very quickly, in terms of your degradation products, have you considered trying one of the different dihydroxyanthraquinones, like the 1,5 or something, and see if that changes it?
That's a really good point. Yeah, I definitely want to move on to different quinones. So we do have some other quinones used, so that like there's phosphonated quinones that have been shown to have like lower electrochemical degradation rates. So that would be sort of the next thing I'd be moving to. It's just, my plan actually was to look at a whole range of different electrolytes, but I guess I sort of got distracted in my project and it's sort of gone down different paths. But yeah, that would be really interesting.
Sounds good, thank you.
Well, with that, let's thank Emma one more time. So our last speaker for this session will come to us by Zoom, and this is Shuo-Chan Kang, and he, I think it's a he anyway, is coming to us from Jeonju University.
Hello, can you hear me? Hello. Hello. I'm not sure I'm connected. Is there anyone indicate I can start now? Hello. The sound. Can somebody talk? Hello, should I start? I can't see this. Can somebody see a word? I cannot see the chat panel. Don't know why. I'm sorry. Okay. I can hear some sound. Can somebody speak?
I can speak on the microphone.
Okay, I can hear you. Okay, I can start now, right? Can you see my screen?
Sorry.
Can you see my screen?
See your screen. We're just trying to get your audio to come through.
Can you see the screen now?
Speak first, please.
Hello? Hello, everyone. Can you see my pictures, my PowerPoint?
We can hear you.
Right? Can I start?
Go ahead and start.
Okay, thank you very much. I'm sorry. It's very difficult. It's difficult for us. And hope everyone is patient enough to stay here. It's really a great honor to be invited to give a talk at the ENC. But it's very unfortunate that I cannot be in Florida in person to meet everyone. And you can see it's quite technically challenging for me to give this talk, but I can still very excited to feel the presence in such prestigious event. So what I'm going to talk about today is about the nanocrystals, or the so-called quantum dots. So the quantum dots are consisted of an organic core of a few nanometers, and the size of the nanocrystals can be adjusted to give a very bright and visible, a pure and visible emission of a tunable wavelengths. The quantum dots are emergent materials for displays, photovoltaics, or catalysis. The key structure features of quantum dots are their inorganic core and also a surface layer of organic ligands. So there have been a few NMR studies on the nanocrystal systems. For instance, Amos-Lee's group have used the DMP to study the structure of the inorganic core. And also Rossini's group have done some excellent multidimensional spectroscopy on these nanocrystals. However, in our group, we are focused more on the organic layers of the nanocrystal surface. In fact, the ligands are just as important as the core, because the ligands control their solution properties, such as solution dispersity, and they determine the self-assembly in the solid phase and affect the electron transfer between the nanocrystal and the substrate. And because the ligands are flexible and disordered, there are very few techniques can provide direct characterizations, but NMR. So in our previous works, we studied the coordination structures of the ligands on nanocrystals. This study relies on the C13 chemical shift and the DFT calculation to show that the different facets prefer different coordination configurations. For instance, the 100 facets prefers the chelating conformation, while the 111 facet prefers the bridging configuration. In another study, we try to solve the surface morphology of the mixed ligands on nanocrystals. This study utilized the codex pulse sequence to decode the homonuclear coupling between the C13 labeled ligands. For the different partition morphologies, the overall coupling strengths of the C13 can vary notably, and therefore we can identify the characteristics of surface morphology, and we show that the aerial partition is evident for the spherical nanocrystals. Besides the coordination and the partition morphology, the interaction between ligands are also very important. Here, today, I'm going to introduce what we do how to calibrate interactions. Here, we look at the two possibilities. One is the interaction between the ligands themselves, that's called ligand-ligand interaction. These are dispersion interactions between the hydrocarbon chains. These ligand-ligand interactions affected the packing strength of in the solid phase. Also, the second is the interaction between the ligand and the surface of nanocrystals. The ligand surface interaction affects the dynamic equilibrium of ligand exchange when the nanocrystals are in solution. So let's look at the ligand interaction first. The intermolecular dispersion interaction is actually very weak, and it hardly affects the chemical shift of NMR signals. So we decided to study the dynamics and get an indirect measurement of this interaction. The deuterium NMR is probably one of the most convenient strategies to study the dynamics in solid phase. For some ligands, the deuterated version is commercially available. So we can put these deuterated ligands on the surface of nanocrystals and do the deuterium NMR. This is an experimental quadrupolar pattern of the deuterium. This can be broken down into three different contributions. For example, the broad peak pattern that corresponds to the CH2 unit under strong packing, probably in a glassy state. And also the cathedral-like pattern, a little bit narrower, that correspond to the CH2 undergoing TGG rotation, the trans-Gauss rotation in a partial confinement. And also the sharp peak in the middle that correspond to the free CH2 undergoing like a wide angle coherent diffusion. That means it's without any restriction. So we can get three contributions, and then we perform this deuterium NMR on different samples, either with pure ligands or the nanocrystal with mixed ligands. The mixed ligand crystals consist of ligands that are partly long and partly short aliphatic chains, like one with 22 units or the one with 14 carbon units. So either the long ligand or the short ligand can be deuterated for NMR investigation. You can see from the patterns, we can see the similarities and dissimilarities between the long and short ligands. So when they are on the pure ligand, pure nanocrystals, the outer 5 units are free for both long and short ligands. But when the 2 ligands are mixed on a single nanocrystal, the outer 14 units are become free for the longer ligand. But the changes in the shorter ligand are relatively small. So based on these results, we can make a schematic illustration of the ligand layer on this nanocrystal. While the deuterium NMR is very helpful to offer the general picture, it is relatively difficult to derive more elaborate values of the motional amplitude. The dip shift experiment can measure the residual CH dipolar coupling after motional averaging. Based on classical analysis, we can calculate the order parameter and get the motional amplitude of the CH bond. However, here I would like to introduce the dynamic volume concept that goes beyond the classical dynamic analysis. This dynamic volume analysis concept hypothesizes that the confinement volume by the that as it is accessible by the dynamics motion is inversely proportional to the intermolecular interaction energy that leads to the confinement. The motional amplitude. So with this in mind, we can use dip shift to provide the assessment of the dynamic volume. So here we assume the opening angle of the CH bond motion is equivalent to the angles of the segmental motion. So with the geometry of this ligand and also the angle, we can calculate the dynamic volume of a single CH2 unit. And then we can derive its energy. So for the interaction energy of the whole ligand, it is a summation of all its carbon units. Actually, this paper we just submitted online. So we obtained the interaction energy for the respective long and short ligands. This analysis can be performed on the selectively labeled samples. So like one ligand is protonated, the other is deuterated. So we can see the interaction energy of the long ligand is much reduced for the ratios, for different ligand ratios, especially when they like a 0.4 or 0.5 ratios. But the interaction energy for the short ligands are very much the same. So this is very consistent with our studies with deuterium NMR. However, the selective deuteration is quite costly. So we try to do a simpler measurement on samples with like both protonated ligands. Of course, for both protonated ligands, we want to be able to separate their individual contributions. Nevertheless, the simple analysis that gives correlates very well with the results of the partial deuteration. So the black line is based on the both protonated experiments, and the green line is the summation of the selective deuteration. So this indicates that the dynamic volume analysis is pretty robust with respect to the experimental uncertainties. So we can derive the interaction energy, and we can see it has a direct impact on the collective properties of these nanocrystals. For instance, interaction is related to the solution dispersion as well as the melting process. For example, the dispersity, mirror dispersity has a linear correlation with the energy, and also the melting points has a linear relation. That indicates the consistencies between the bulk measurement and the dynamic volume analysis. So this results show that the enthalpy and the entropy that we derived for dispersion and melting are almost equal. It tells us the dispersion process and the melting process of nanocrystals are fundamentally equivalent, because they both need to break the intermolecular interactions between the ligands. So the above dynamic volume analysis rely on the dip shift experiments. But can we predict the interaction energy without NMR measurements? Here we derived a geometric model of the dynamic volume for surface ligands. The dynamic volume of each carbon unit are shown as the disks here. The bigger the volume, the weaker the interaction. The model considered the influence of ligand length and also the ratio, using the empirical parameters according to the measurements of only a few representative samples. So this semi-empirical model shows excellent agreement with the results obtained with experimental dip shift. Then we can use this model to calculate the interactions of samples with different ligand lengths and ratios. For here, there's no NMR experiments performed. We just use this semi-empirical model itself. So the calculated interaction energy follows the expected thermodynamic equation for the solution dispersity. This demonstrates that the general applicability of the dynamic volume concept. I think in principle, this concept can be extended to other types of ligands and also other structures with flexible components. And if you are interested, you can refer to this manuscript that we just submitted. So the second part of our study is to trying to calibrate the ligand exchange on nanocrystals in solution. So when the nanocrystals are in solution, the surface ligands are in the dynamic equilibrium of the bond and the free states. The bond and free ligands are in constant exchange with each other. So to mirror the exchange, the first to separate their signals in solution. So previously, this was done like in ligands with a double bond. Because the double bond will show a difference in their chemical shift when it is bound on the nanocrystal or when it's free in solution, like here, the red and the blue color. However, like in more general cases, the ligands doesn't need to have a double bond. They can be all saturated carbon hydrocarbon chains. So for example, here, the signals of these hydrocarbon chains in solution will strongly overlap. So we cannot separate from the chemical shift whether they are bond or free. But there are other ways to distinguish the signals. And we think probably the diffusion coefficient is the most convenient way to distinguish the free and bond ligands. So the bond ligands have much reduced diffusivity because it's a much larger particle in solution. So the figures here showing the dephasing curves of the bond and the free ligands under the pulsed field gradient. And the difference is big enough for us to separate their individual populations and to mirror the exchange rate with this kind of exchange equation. Of course, also the relaxation needs to be considered during the NMR pulse sequence. So we compare the three different.
Dr. Kong, only you can. Got it. You're at 3 minutes and getting into the question period. Just
okay, I will try my best and finish this very soon. So I try the three different methods to mirror ligand exchange. The first is the diffusion 2D correlation with two stimulated echo blocks. The exchange rate could obtain from the cross peaks of this two diffusion species. But the 2D method is very time consuming. For a single plot, we need many hours. The second is a filtered exchange experiment, also called a FAXI. The FAXI use exactly the same pulse sequence, but use the first block as a filter to filter out part of the signal to create a non-equilibrium magnetization. The FAXI can be much more efficient than the 2D, but the filter reduces the signal intensity dramatically, and it still needs multiple mixing time to get an exchange rate. Finally, we can use the just a simple pulse gradient STE, PGSTE experiment. With a careful adjustment of the experimental parameters, we can measure the exchange with only two sets of experiments. One is with very short mixing time, and the one with longer mixing time. Because the requirement of the gradient pulse, the upper limit for the measurable exchange rate is about 200 Hertz. So we mirrored this, use this PGSTE to mirror the ligands with different chains and different functional groups. For example, the carboxylate and the amines. We can obtain the activation energies for their study of the kinetics. We can also obtain the equilibrium constant and measure the versus temperature and then get the thermodynamics of the change, and also obtain the enthalpy and entropy changes. So in summary, we presented two works. One is using the dynamic volume model to calibrate the ligand-ligand interaction, and the other is use a diffusion-based method to measure the kinetics and the thermodynamics of ligand exchange. And finally, I would like to thank my colleagues and especially my students, especially Zhenhong Pan, Weichun Cao, and Xiaoqi Zhou, who did this work. And thank you for your attention. And if you have questions.
Thank you. Thank you, Dr. Kong.
Okay.
So I know we're approaching overtime, but time for maybe a brief question or two. So I'll take the chair's prerogative and ask one from the room. So when you have these deuteration, these deuterated species, of course that will affect the van der Waals interactions, the ligands on the surface. And so in the modeling that you're doing, are you taking account for that effect overall?
Yeah, it can affect this van der Waals interaction, but we didn't consider that taking into account. This is also just a numerical models, so it's not like molecular dynamics models.
Okay. Yes, please. There's a question from the room. You step to the mic. Who you are.
Hi, this is Rick Dorn from Aaron Rossini's group. So one of my questions is, are you able to look at different type of facets and their exchange? So like I think a lot of them you're looking at spherical nanoparticles, but if you thought about looking at like platelets or anything?
Yeah, very nice question. Thank you for asking. Actually, this work we've done right now is only for the spherical nanocrystals, but we can try nanocrystal with different facets. And actually, we are doing that because we can prepare these nanocrystals with different facets.
Thank you.
I think we can show some interesting results probably in the future. Yeah.
Well, with that, let's thank Dr. Kong for his presentation, and we're going to coffee break next. Thank you for attending remotely. And thank you all for being patient with some of the technical hiccups. We know that it's difficult being a speaker on Zoom, not knowing what the audience looks like, and vice versa. Thanks to the tech crew for working us through this session. You guys are good. All right, we'll see you after the coffee break.
See you.